All right, let's continue for our discussion in Chapter 5. As you can see here, Chapter 5 is closely related to the propagation. Wave propagation toward in different material. What happens? You have reflection and transmission at the interface of different material, and so they are the basis. They are the basis for research on propagation topics, which can be important for my students. All right. As you know, my research area is antenna propagation, or the propagation part, especially the radar cross-section related topics are closely related. Of course, the research in propagation. All right. So the next topic we like to see is reflection and transmission in multilayer material. Of course, in real world, you probably wouldn't be able to look into target with aligned layers. So it's kind of a simplification of real environment. It's a simplification. It's an approximation of a real environment. We simplify the propagating environment into parallel layers. Parallel layers of consistent thickness, so that the analysis can be conducted in analytical way. But the real problem usually don't have 没有像这种千层蛋糕这么漂亮的那种叠层的结构了。Actually, in real world propagation problem, you probably won't be able to find this kinds of structure. Okay, but somehow they can be approximated as layer structures. Okay, so here is the reflection coefficient between just two medium. So you know that it's for two medium, medium 1 and medium 2, the reflection coefficient is eta 2 and minus eta 1 over eta 2 plus eta 1. And the things important here is the translation of the reflection coefficient. So use the description for propagation delay. So if you are standing some distance, so here is the boundary. The boundary is here is the reflection coefficient at the boundary. This is the reflection coefficient somewhere in front of the boundary. So you need to add the phase adjustment, exponential J2 times beta 1Z. So suppose here is Z equal to 0. So some distance L in front of the boundary, in front of the discontinuity. So you substitute Z with minus L to this, then you end up with gamma B, the reflection coefficient of the boundary, times exponential minus J2 times beta 1L. Suppose you are in a lossless medium. So you simply adjust the phase change, the phase variation to and back toward your observation plane. So the blue dashed line is your observation position. So you're looking into, so you kind of translate the reflection coefficient from the boundary to your observation plane using this phase change relationship. Okay? And if you are propagating in lossless medium, then the input impedance can be substituted with intrinsic impedance of the region. Okay, so here you use eta 2. Okay, to represent the next medium. And the input impedance, by definition, input impedance, as I already said, impedance, Z is the ratio of E field over H field. So the input impedance at this location is the total E field over the total H field. So it can be decomposed into the summation of incident E field and the reflected E field over incident H field and the reflected H field. The reflected E field and reflected H field can be substituted with EI times 1 plus gamma Z. Use the reflection coefficient and its translation to represent the, ER is EI times gamma Z. Use the translated reflection coefficient to represent your reflected E field. And you can do the same for H field. But you need to use the so-called current reflection coefficient 所以多一个负号比较讨厌那个反射波的那个 H 会转方向You need to be aware that the reflected H field is inverted at the boundary. So you have the minus sign over there. And the first thing is the intrinsic impedance of medium 1. So it can be substituted with eta 1. The other things, the 1 and the reflection coefficient gamma, can be used what we have in the previous slide. The translated reflection coefficient. And you can further simplify this relationship like this. And with some manipulation of the edge box sum of this, you end up with this. This is important, and this can already be seen in your undergraduate electromagnetic. 你大二大三上的那个电磁学里头一定有这个式子所以事实上它不是那么的复杂了That is the input impedance at a position minus L can be written like this. As you can see here, it is a composition of eta 1 and eta 2, and the tangent of beta 1L. Okay. So that's something you should keep in mind. You don't have to memorize it, but you have to keep in mind that the input impedance, the reflection coefficient can be translated. The input impedance can be translated as well. Okay, so this is important topic for microwave circuit design, for microwave engineering, for transmission line design. 假如你的工作跟微带线传输线跟传输线电路有关的话，这个东西你不可能不知道不可以不知道 OK And so let's make our life a little bit harder. Let's make the problem a little bit more interesting. In the previous slide, we have 2 medium. Here we have 2 media. Here we have 3 media. 3 media. And to make it a little bit easier, we have one material sandwiched between 2 material. 2 material. So the very last material is kind of semi-infinite. 往右边无限延伸. Number 3 material is semi-infinite toward the positive z direction, and number 1 material is also semi-infinite toward the minus z direction, while number 2 material has a specified thickness of d. Then you can be translated into a 3 transmission line problem or a 2 transmission line problem with a termination. So here we try to replace the problem with simpler transmission line representation. And there, so what we want is reflection coefficient on the left-hand side. Based on the description of this sandwich structure. There are different approaches to solve this problem. And the first one, I would like to refer it as 推平面法哦。这个应该是我自己写的哦，这我自己讲的 ，OK。哦，但我不太确定课本上是怎么写了哈。第一种方法哈，第一种方法。And this is kind of the analytical solution. We can't try to analytical solution. So let's see what happens in this three-layer structure. You have the incidence from here, you have reflection from here, you have transmission into medium 2, and the transmission into medium 2 will find another interface here on the right-hand side, z equal to 0, and then you will have a transmission in medium 3 and reflection in medium 2, like this one. And the reflection in medium 2 will end up more reflection in medium 2 toward and the propagating direction will be changed. And some of the incidence of this part will end up as transmission toward medium 1. So it should be add up with the direct reflection of medium 1. And this process will goes on and on and on. So actually you have infinite number of terms here. For the total transmission on the right-hand side, total reflection on the left-hand side, you actually end up with infinite series. Okay? But because the property at the interface are known, so you should be able to find the analytical solution for total transmission and total reflection. Here is, well, actually you can find the total reflection. Total reflection. Well, actually, this is the analytical solution of your total reflection from here. 课本上没有把那个详细过程完全写出来那个会有点复杂所以我们直接抓结果。So this is a total reflection. So it actually can be solved analytically. So you can substitute gamma 1, 2, gamma 2, 3, and substitute with the phase change of due to the thickness d to find the actual solution of this component. But you can have a simpler solution of this, providing that gamma 1, 2 and gamma 2, 3 are small. What is the implication of this description? 什么叫做 gamma 1, 2的大小跟 gamma 2, 3的大小很小？也就是材质1、材质2之间的性质差异没有很大，它的介电系数差异没有很大。材质2跟材质3的介电系数也没有差很大的话，那么左边的 analytical solution 可以被简化成就分子的部分好了。因为分母的部分你有一个 gamma 1 you have the gamma 1, 2 and gamma 2, 3 product in the denominator. And as long as gamma 1, 2 and gamma 2, 3 are both small, the product of the two will become an even smaller number. Therefore, they are less important. So as long as the difference between median 1 and median 2, the difference between median 2 and median 3 are small, then the solution can be simplified just gamma 1, 2 plus gamma 2, 3 times the phase adjustment. Okay? The result will approximate what you have in analytical solution. And this is usually the case for radon. Okay? So that's the reason why in the previous slide we have proposed a scenario of antenna and radon. That means median 2 is the radon. And you may have antenna over here, and here is the free space. You have free space on inside median 2. And median 2 is usually the radon is usually made of low permittivity material with rigid structure 也就是说，雷达因为它的目的是什么？保护天线不要被风吹，不要被雨淋，然后它又不要影响电磁波的进出所以通常雷达的材质会是低介电系数的塑胶材质或者是那个树脂类或者聚合物之类的材质低介电系数的塑胶材质所以基本上它的 permittivity 大概落在2到4之间当然跟1跟空气会有点差距但差距可能不算太大的话，那么你可以用这一个式子去趋近它。当然假如说你那些材质的参数都知道其实你把这个 actual solution 算出来不会太困难OK， 不过这是三种的了所以我讲的第一个方法是推平面那个推平面其实就是像传输线理论里头一样，你把反射系数从后面往前推所以才叫推平面法。那第二个方法就是边界条件法找出边界上面的电场关系，然后求减多项式，这也是一个方法。那它算出来的也会是 analytical solution。那第三种方法叫 ray tracing， 那我们等一下会看。那它算出来的不是 analytical solution， 它因为就看你算的那个 term 越多越准所以它是一个 approximate 的一个方法approximation 的一个方法But so the first solution, the first method is kind of similar to what we done with transmission line. So you find out the reflection coefficient and input impedance of different places as it move along toward your desired position. The second method is the boundary the second method is trying to solve it using the boundary condition, which shall give you the analytical solution as well. And the third method is commonly used in propagation problem. It's referred as the ray tracing method. So you kind of analyze how the electromagnetic waves goes front and back in the multilayer structure and try to find out an approximate solution for this problem. Okay, so as you can see, it can becomes the direct reflection. So the direct reflection part is the incidence times the reflection coefficient at the interface gamma 1, 2. And the second terms can be traced from incidence, transmission, reflection, transmission. So the second term is tau 1, 2 times gamma 2, 3 times tau 2, 1 times the exponential minus j2 theta. So the very last term is the propagation delay due to going forth and going back. And here you have the third term. So you can actually trace the path of each propagation. It goes into, here's the transmission, reflection again, and goes out as the third term. So on and so forth. You can have higher order terms sequentially. So here you have the first term, second term, third term, fourth term. As you generate more and more terms, you can find out that you eventually will have an infinite series, 一个无穷的米级数. So actually you can find out the analytical sum of the infinite series, or you just based on the fact that higher order terms tend to converge to 0. Why? Because reflection coefficient is something smaller than 0, right? smaller, something smaller than 1. Okay, so the higher order term, which experience more and more reflections, will become smaller and smaller, and it will go to 0. It will converge to 0 eventually. So, which means you don't need to collect all the terms. You don't need to collect all the terms. You can use just the first few terms, first 2 terms, first 3 terms to represent the general behavior of your ray tracing result. So, providing that the difference between median 1 and 2, the difference between median 2 and 3 is still small, then you end up with this result. That will be your principal terms, the dominant terms for your total reflection. So if you're interested, you can continue the discussion over here. You can continue the discussion over here and find out that. So if the product of gamma 1, 2 and gamma 2, 3 is much smaller than 1, 这个我记得应该是极小于1了，much smaller than 1, then you will end up with a reflection coefficient like this, which is the same. The first 2 terms is enough to describe the dominant terms of this 3-layer structure. This 3-layer structure. Okay, and it should be approach the result of your analytical solution. So this is the analytical solution. If you carry out the infinite sum, carry out the sum of this infinite series. Okay. And here's some practice. So according to the relationship, you can have a 0 reflection, no reflection. You can achieve 0 reflection, providing that the thickness of a median 2, the thickness D of median 2 is correct. Okay? You found that if you look at this requirement, because gamma 2, 3 is the inverse of gamma 1, 2. It's the negative, not inverse. It's the negative of gamma 1, 2 because if you have, I'm sorry. This is not the radon problem. Okay, I'm sorry. This is okay. This is the quarter wavelength transformer. Sorry, no. 不好意思，这是 quarter wavelength transformer。为什么？因为它的1号材料是空气，2号材料是介链系数为4，相对介链体为系数为4的材料。那这个是 epsilon 2，所以我们不知道 epsilon 2的介链系数，我们也不知道 D 的厚度，但是我们想要透过 epsilon 2跟 D 的决定来去达到 matching。So we attempt for this 3-layer structure, we attempt to achieve 0 reflection by manipulating the material property and the thickness of layer 2. So you can choose epsilon 2 and you can choose D2. Okay? So to achieve 0 reflection, we need to achieve what? We need to achieve that. So one condition is that if J 2 times beta 2 times D equals to pi, if this is equals to pi, equals to 180 degrees, then the exponential end up as -1, Then we may be able to solve this problem. Okay, so we first choose to have 2 times beta 2D equals to pi, then we end up with lambda, with D equals to 1/4 of lambda 20. That is the wavelength within within median 2. So we see, you can tell this is actually the so-called quarter wavelength transformer. All right. So if D is a quarter of the wavelength in median 2, then exponential minus j pi end up as -1. So you have gamma 1, 2 minus gamma 2, 3 equal to 0. To satisfy the condition that this thing goes to 0, then gamma 1, 2 must, the magnitude of gamma 1, 2 must equal to gamma 2, 3. And if you substitute the reflection coefficient of gamma 1, 2 and gamma 2, 3, you end up with this relationship, that is gamma 2 to the square equals to the product of gamma 1 and gamma 3. 我在讲什么 eta 了，对不对？对不起，我刚刚整个都讲错。哦，不对，前面是 gamma，OK， 这边是 eta，OK。You end up with, you substitute the intrinsic impedance with the within the reflection coefficient. So you see the intrinsic impedance of median 2 should equal to the square root of the product of the intrinsic impedance of median 1 and 3. So supposing that median 1 is free space, so eta 1 equals to eta 0. Eta 3 has a relative permittivity of 4, so the intrinsic impedance of eta 3 is half of the intrinsic impedance of the free space. Then you can solve for eta 2 as eta sub 0 over square root of 2. So epsilon R2, the relative permittivity of median 2 is 2, and the distance is the guided wavelength within the median 2, which can be determined by the specified frequency, that is 10 gigahertz. So you end up with a thickness of half a centimeter, 0.53 centimeter. And so this is the example for a quarter wavelength transformer. In this slide, the textbook would notify that the quarter wavelength transformer is good, is valid, but it's only valid for a specific frequency. So it's actually a narrow-banded design. Okay. So according to your requirement, if you only need to achieve matching condition for a specific frequency, then you can easily use quarter wavelength transformer. On the other hand, if you want to achieve matching for a broadband signal, then you may need to seek assistance from other techniques. The quarter wavelength transformer technique by itself is a narrow-banded technique. 所以你需要一些 And what happens if you want to do a broadband match? Well, you trading performance with structure complexity. 所以对于工程的问题，你就是 trade off。所以你要达到更好的宽频的匹配，那结果就是你的 matching 的 circuit 会变得很复杂，所以这边讲的就是 higher order 的 design，就是 more complicated structure。So usually the solution to broadband problem is higher order design. Okay. So here are a few examples for higher order design. One is using the multi-layer median, or by analogy with transmission line design to achieve very broadband matching. What you can do? Taper transformer 有没有听过？今天假如说你有一个50欧姆的传输线，这边是一个100欧姆的传输线。假如你是要 只要做到特定频率的 matching 的话，那你就是用一个刚刚讲的 quarter wavelength transformer 嘛。哦，那假如说你要1 GHz 到10 GHz 都 matching， 那怎么办？那我会用 taper transformer 啊，就是把两边连起来，但是你要拖得很长，你拖得越长，它的频宽越好。所以你是用框间去换频宽，你拖得越长，那其实就是一个越高阶的设计，你的 transformer 就相当于越高阶。啊，所以像这一个设计怎样，把它分做好几层，啊，每一层跟每一层之间都差一点点，啊，每一层跟每一层之间的 intrinsic 都差一点点，所以它的 intrinsic 的 because in this case you try to accomplish broadband matching. A very broadband matching. So the method is adopt a multi-layer structure, a higher order design. So for this multi-layer structure, the difference between the permittivity in adjacent layer is very small. So as long as you can add many more layers with small differences, then the reflection can be minimized. The reflection between each layer can be minimized. So it's very similar to the so-called taper transformer in transmission line design. Oh. What is the price? The price is the size of your transformer. Oh. So for quarter wavelength transformer, for single frequency, you just need a quarter of wavelengths. But this one may take a few wavelengths, a few wavelengths, 好几个 lambda 你才能够做出来。So 这边我就不细讲了啦，哈，这边我就不细讲了，因为它的假设哈 ，the assumption is if you have a multi-layer structure, you assume the difference in each layer is small, so you only account for the first term. You can only account for the first term. Then it's possible to design, to achieve a matching design for a very broad band, as long as you have very many more layers with small difference between each adjacent layers. Okay. And here you try to specify that each slab is quarter wavelengths for the center frequency, and the thickness of each slab is a little bit different. Okay, and because of the quarter wavelengths property, so the reflection, the sign of the reflection will alternating between positive and negative number, of some small positive and negative number. So the total sum of the reflection coefficient is still a small number. And to accomplish it, you can do the so-called binomial design or Chebyshev design, as you've seen in filter designs. Okay, in filter design, you have the so-called Chebyshev design and binomial design. So here is kind of a review of the binomial design, all right? So I won't go into the detail of this, so let's just check up the result, okay? Check out the result of binomial design. So, well, what is the binomial design? Okay. So let's go to this slide. This is the so-called binomial design, okay? So it touch the matching point at the center frequency, required center frequency once. And the bandwidth is broadened with higher order design. And the other line is the so-called Chebyshev design. So as you can recall from your undergraduate circuit design courses, the Chebyshev design will touch zero reflection several times according to the order of the Chevy-Chef design. In this case, you have just a two-section Chevy-Chef design, so you touch zero reflection twice. And in between, the reflection coefficient will rise a little bit, but as long as it's smaller than your specified reflection coefficient criterion, as long as it's smaller than your specified reflection coefficient magnitude, well, then you should be safe with this Chevy-Chef design. So here is another, so this is just two-section binomial. So the broadening in bandwidth is visible, but it's not that obvious. But with this design, so as you can see, you have a higher order Chevy-Chef design, so you can achieve broadband matching with very high order design. So Chevy-Chef design is also referred as equal ripple design. Okay. And all right, I won't go into the details of Chevy-Chef design. It's derived from the Chevy-Chef polynomials, as you can see from its name. And if you're interested, you can look into this. So the last thing I would like to mention is the absorber. Okay, so anyone doesn't use the anechoic chamber? I suppose most of you have seen the anechoic chamber, 对吧？反正无反射实验室有去过嘛，对不对？有没有人没去过的？只要没去过，只要有去过的话，你应该看过我图上左边这个东西啊，这是什么东西 ？Absorber. So it's actually It's a match device for propagating wave. So 所以你一定有自己问过说，为什么 absorber 长这个形状？为什么 absorber 长这个形状？第一个啦 ，What is the composition of absorber? It's foam, FOAM, 发泡海绵 with doping, with conducting material. So actually, this thing is not good for your health. It contains tiny particles of tiny conducting particles. So this tiny conducting particle is not good for your inhalation system. 对于呼吸道来讲不是很好的事情因为它是很小的粉尘里头有一些掺一些很小的粉尘。Because of the doping conductive particles, so the conductivity of the absorber is kind of varies gradually as you propagate into it. So if you are at the tip, the effective conductivity is small. If you are at the bottom, the effective conductivity is larger. So it's very similar to the so-called taper transformer. So because at the very end, the very bottom of the absorber is what? Is your metal plate of your anechoic chamber. So the conductivity, so the let's describe it in terms of resistivity. Okay, so the resistivity of the metal plate is 0. But at the front, you have a 377 ohm for your free space propagating wave. So you need to provide a transition from 377 to 0. So the shape of the pyramid of the absorber provide a spatial transition in terms of the effective impedance. Okay. So therefore, the absorber height is proportional to the lowest effective frequency. The lowest effective frequency. In general, in principle, if you have a pyramid absorber of 30 centimeter, then according to the half wavelength principle, the lowest effective frequency for this absorber is what? 500 megahertz. Because the wavelength of 500 megahertz is 60 centimeter. So if you have a absorber of 30 centimeter, then you're supposed to absorb electromagnetic wave down to 500 megahertz. Okay? So the bigger the absorber, the lower is its effective absorbing frequencies. All right? And due to the time limit, I will just say that this one is referred as the Salisbury screen. 只要你去查一下，有一个名词啊，这个东西叫做 Salisbury screen 哈。那它事实上就是 quarter wave transformer。对不起，我讲错，它不是 quarter wave transformer， 它是那个什么？它是那个什么？这个东西叫做 Salisbury screen 哈。我不知道各位有没有看出来，他用的技巧是什么？他用的技巧其实类比于传输线啊。In transmission line theory, if you have a transmission line terminated with a short, then because of the presence of total reflection, you have a total standing wave, right? Then because of the total standing wave, if you are a quarter wavelength in front of the shorted region, of course, the input impedance at the short is 0. What happens about the input impedance at a quarter wavelength? It's infinity. It's like an open. Okay, because of the total standing wave. Here you have 0 voltage. Here you have 0 current. So the impedance here goes to infinity. So it looks like an open with a quarter wavelength spacing. So according to this principle, without the presence of a 377 ohm resistor, the input impedance here is infinity. Then you provide a shunt combination of resistor of 377 ohm. So what is the combined resistance of 377 ohm with infinity, with open? The resulting resistance is 377. Okay, so with the Salisbury screen technique, you can achieve perfect matching. Unfortunately, the Salisbury screen is a narrow-banded structure. So it's only valid for one frequency, and it's only valid for normal incidence. So if you have an oblique incidence, if the wave is coming not from the front, but with an oblique incident angle, then the Salisbury screen is not that effective. So in fact, in anechoic chamber, we do have tapered transmission line approximation. We use pyramid-like absorber to perform gradual transition in the reflection coefficient, in the input impedance. Okay, so here is a one wavelength example of one wavelength design. If this is 377, this one is 185, 377, something larger than 377, and even larger. So with this taper structure, multi-layer taper structure, you can achieve broadband matching for propagating waves. All right. And I provide some discussion from the textbook about the metamaterial, and it's, as you know, it's a hot topic, and unfortunately we probably don't have time to go through the metamaterial section, so I will encourage you to look into the slides yourself. It probably won't appear in your midterm exam, but it's do you some good. It can do you some good by looking into the discrete introduction of metamaterial. So let's just go through this slide. The first quadrant is the so-called double positive material. This is the description for ordinary material. That is, you have greater than 0 permittivity and greater than 0 permeability. So it's also referred as right-hand material, which means the wave propagation in this kind of material, the E field direction, H field direction, and propagating direction follows the right-hand school rules. And based on this definition, you can find other definitions such as ENG, epsilon negative material, magnetic negative material, and double negative material. Usually the so-called left-hand material. Well, this one is the ferrite. This one is, example of this one is plasma. 就是正负离子存在的那个电浆电浆体里头有可能会出现这种状况。这个的话比较像磁性材料里头会出现的状况。然后它们伴随的都是 evanescent wave，它的电磁波在这两种材料里头都传不太下去，所以我们才称之为 evanescent wave， 快速的就会衰减掉。那这边是 epsilon 大于0 μ 小于是 epsilon 小于0 μ 大于0。所以电磁波在这两种材料里头都传不远了那实际上你是可以有这种材料的像磁性材料ferrite那边的话有例子是电浆。好了，那所谓的 metamaterial 主要是看这一块，它就是 μ 小于0 epsilon 小于0所以称之为 double negative， 或称之为左手也就是说它的相位变动跟自然的传播情形比较的话，它比较像是倒着跑的，所以它的相位变动是反着走的所以 because the phase changing direction or phase changing sign is as the opposite of ordinary propagating wave, so it's referred as the left hand or backward propagation material. All right. So which means that you can have an effective permittivity and effective permeability that are smaller than 0. The ways to achieve that is using very small structure made of metal structure. Usually it's made of metal periodic metal structure with periodicity much smaller than the wavelengths. So that is a requirement. But as you can see, in recent research, what concerns me is that the term metamaterial is used. I'm afraid that in some research, the term metamaterial is not used properly. So 有的时候它就是一个共振结构有的时候一个结构它也说跟你说它是 metamaterial。那其实都不符合定义啦，因为我们讲的 metamaterial 它应该是一个周期性结构，你起码要有几个吧，好不好？要有几个，不能只有一个啦，只有一个我们不能说它是 metamaterial。 然后再来就是大小，假如它的那个周期性结构的大小比跟波长差不多，在 the same order 的话，其实也不太 qualify 说它是 meta material 啊，所以这边你看到它的 requirement 是要它的那个尺寸要极小于波长啊，多小？起码你要1/6还是1/10的波长以下，好不好？你假如说是半个波长的结构，它其实不能算，好不好 ？OK， 那其他的东西我觉得有些效果是腐烂的，所以要小心啊。有的时候这种新名词，趁大家不懂的时候，有人会去乱讲哦。OK， alright, so I'm suppose that you can look into this kind of description, and here's some of the result. Okay, you see the diffraction. The direction of diffraction is inverted due to negative permittivity. Due to negative permittivity. And here is the result. You can see that outside of the lens, the phase front is about the same, which means the wave propagating through this lens without apparent phase change. 这个是左右手传输线在用的一个，有的时候会做法，就是让它那个，这其实你们马老师做很多了，马老师做很多，它其实就是让一段传输线它的那个相位不要动。那你只要能够做到宽频的话，那其实可以设计出一些有趣的元件，对，让它那个相位，假如你相位不要动，你就有可能让这个元件变得比较宽频了，可是meta material 虽然被讨论的蛮多的它是最近这20年来电磁学，最近20-30年来电磁学一个蛮重要的一个发展It's a hot topic in electromagnetics. But what is the problem about meta material? The most fundamental problem is loss. The signal loss in meta material. Okay. So usually the component or circuit component made of meta material usually suffer from substantial loss as the wave or signal propagating through it. 好吧，大概是这样子吧这边的那个立体油漆，你会看到它的那个 loss 其实会随着，其实是蛮显著的，相较于一般的右手传输线。好，不好意思，我们今天拖得比较久我们今天到这边 ，OK。好吧，作业交一交吧，我们今天谢谢大家。